All right. So the thing with stars is, one, they're really far away. You can't just go take measurements, right? Another thing is they're crazy, crazy hot, right? Because again, you can't get near enough to take measurements. So ostensibly, we're going to teach all these things about stars. We're going to learn all these things about stars. How can you possibly learn anything about a star that's so far away, and it's so crazy hot, and so massive? How can you learn anything about it?
But what comes off them?
And what is that?
Gamma.
Okay. Some gamma rays. Anything else coming off of a star? Light, right?
Oh, maybe that's it.
Everything, really, principally, almost everything that we learn about stars, we learn about by their light. What do you know about light?
It's bright.
Unless it's not. What makes it bright?
The wavelength.
Wavelength has something to do with something big, but it's not brightness.
Color.
Hmm?
Color.
Color makes it bright.
Not necessarily, but the brighter. Well,
Some colors maybe you see better
How
than
hot it
others.
is.
Pardon?
How hot it is?
How hot it is?
The fusion
No.
and the core.
So-
Don't do nothing?
If I take this,
Says such the gray,
is this bright?
Yeah.
you look directly at it.
Huh?
Said you look directly at it.
Yeah, from here it might not seem that bright, right? But if I go like that, don't do that. It's crazy bright, right? What's the difference between looking at it from where Cody's at over there and me shoving it into my eye? Distance?
The number of photons.
You Google that. There you go. Yeah. So what makes light bright or dim is simply how they're going everywhere else. They're spreading. The closer you get to the source, the brighter it is. Actually, it's an inverse square law. You want to learn about that real quick? Let's do that. So brightness. This is good to know. This is actually really good to know. Whatever you do, light. Let's look at brightness. Okay. So we're going to do. Let's do intensity. And let's do distance. Okay. So you know, the closer you are, the brighter it is, right? So let's go super close and super bright, and we're going to go right up here, okay? Now the question is, what shape is this going to make? As I move away, you expect, as I move this way, what's going to happen to this? It's going to go down, and you're not allowed to answer this next one, okay? But as I move down, if I put, let's say I put I want to look at it here. Where do I need to put my mark here? You want it in the middle? Okay. And if I go here, where do you want my mark?
On the line.
Huh?
On the line.
Make a line? Oh, like here?
Yes.
Okay. So that'd be linear, right? There are plenty of things that work like that in the universe, but light and intensity of light does not function like that. It's what we call an inverse square. So the shape of something that's squared is a parabola, right? So think of something like this, right? So we're going to do only the inverse part of it, this half of it here. We're going to ignore this, okay? So it actually forms this shape. Okay. So here's how that matters. If I get twice as far away, it doesn't get twice as dim, it gets 4 times as dim. If I get 4 times away, it's not 4 times as dim, it's not 8 times as dim, it's 16 times as dim. If I move 10 times away, it's not 10 times dimmer, it's 100 times dimmer, right? So, the opposite is also true. The closer I get, as I get a little brighter, it gets exponentially brighter, right? So this is classic, and there are a lot of things in the universe that work like this. Sound works like this. So you got your headphones in your ear and like you're jamming, right? And you take them out, and yeah, we can all hear it because you're making yourself deaf, but we can just barely hear it, and you can just barely hear it. But also, you put them twice as close, it's 4 times louder. You put them twice as close again, it's 4 times louder again, right? Until it's in your ear and your bones are shaking. So brightness is like this, sound is like this, right? All right, so all that was because we asked the question about light. Well, what makes it bright? Or actually, maybe I didn't even ask that. Maybe we just talked about brightness. Other aspects of light that we want to consider. You mentioned, somebody say wavelength? Or what did we say? Wavelength, okay, wavelength. Another property of light, that's probably where we're probably talking about properties of light, right? So brightness, wavelength. Another one is going to be its, well, we can consider its velocity. And another one we can consider is its frequency. When we say velocity, what we mean here is speed, okay? What's the speed of light? It's fast. How fast?
3.14 something.
3 something, right? You can just say c, right? Equals mc squared. It's really fast. You can Google that. I don't need you to have that memorized. But the thing, here's the thing. What's the speed of yellow?
Yellow?
Yeah, what's the speed of yellow?
Speed of light. The speed of blue.
The speed of blue. Also the speed of fuchsia, and the speed of, brown, and the speed of blue, and the speed of red. They're all light travels at the exact same speed. Here's what we mean by that. If I had a laser here, and it was firing off yellow, and another one that was firing off blue, and another one that was firing off red, okay? And I've got some kind of we're going to have a race, and they're all going to at the same time, okay? In fact, maybe they're all shining, but I've got like a little card in front of them, and I lift the card off, and I've got a photo sensor over here, right? Well, which light hits first? They tie, right? Because all light travels at the speed of light. Period. Okay? But they don't all have the same energy, do they? No. Let's talk about energy a little bit. Okay. I know we live in a digital age, and you guys have phones, and you take a picture, and you can have it on your phone, you can this, and you can that. And when I was a kid, it wasn't like that. You got a camera, and it had film, and you took a picture, and you hoped that it turned out. And you'd find out in about a week after you took it to the photo lab, and they developed it. You familiar with that concept a little bit?
Yeah, I never had to do that.
Okay, so the thing in a photo lab is, if you expose it, if I just took out the film and exposed it to light, it's all going to come out black, because it's all going to get ruined. You can't expose film to light or it gets destroyed. So how do you work with film where you can't expose it to light or it gets destroyed? But how can you see?
Have the light with lower intensity.
Yeah, well, lower intensity what? Not brightness necessarily. Although, yeah, you still don't want it too bright. But you want it to have low energy. And for that they use red light. Red light is the lowest energy light of the visible light spectrum. Okay? Has enough energy and enough whatever that you can see, but not so much that it destroys the film. Okay? On the other end of the spectrum, what kind of light do you need to be careful about exposing yourself to?
Violet.
Well, go past violet.
Ultraviolet.
Ultraviolet, right? You can't even see it, and yet it can give you cancer, right? Because it has so much energy. Right? So all light travels at the same speed, but not all light has the same energy. Let's talk about that for a second. Let's go red, and down here let's go ultraviolet. Okay. What comes after red? Let's follow the rainbow. Orange. And yellow, and green, and blue, and indigo, and violet, and then ultraviolet. And is there light with more energy than ultraviolet? Yeah, do you know any of it?
X-ray.
X-rays, what else?
Gamma.
Gamma rays, good. Okay, good. Is there light with less energy than red light?
Yes.
One of them sounds like red.
Infrared.
Infrared.
I was gonna say black light. Black light.
Okay, we got two more to go.
Microwaves.
Microwaves. Now, isn't that weird to think about? You cook with microwaves. Think about this a second. You cook your food with microwaves, but a single microwave photon has less energy even than red light. And yet it cooks your food fast. So what does that tell you about it? About your microwave at home?
Hot.
Nah.
Good.
If one microwave has hardly any energy, then how am I going to cook my food so fast in a microwave?
Put
Because
multiple.
a lot of them, right? I've got to have a high intensity, okay?
That's
All right.
right.
And then what's up top?
Radio waves.
Radio waves. Okay, so we have organized this in terms of increasing energy, right? It's harder for me to do than you think it should be. Okay, energy. Energy is increasing, right? And by the way, you do have to know these in order. Okay? You must know these in this order. Radio waves, microwaves, infrared, red, orange, yellow, green, blue, indigo, violet, ultraviolet, X-ray, gamma ray. Don't take a picture yet because we've got another line coming. Okay? So this is increasing energy. We're actually going to draw two more lines probably, right? So these are all traveling at the same speed, but they have different energies. How?
Wavelength.
Yeah, they vibrate at different frequencies.
Kinda-ish. That's the idea. So wavelength is definitely let me do my main screen here so that you can see that. Okay, Cody, get up here. Come on. We may have already done this. Well, I know we
You're doing the finger.
gravity and the other thing. You and I are pushing. Did we do this?
Yes.
Okay, we're gonna do this again. All right. So,
Want me to do the long
why
one?
don't you be radio wave? So my radio wave guy, he's gonna have a nice long wavelength. Just nice and smooth. What speed's he gonna travel at?
Lights.
See,
Speed of light. He's gonna travel at C. Come on, Cody. C for Cody. Here we go. You never knew he was so fast. Should have been on the track team. Meanwhile, I'm gonna be a gamma ray. Right? Travel at the same speed. I've got so much more energy. Right? So I've got to have this little tiny wavelength. Let me lead. Actually, you lead slightly so that we don't jam into each other. Ready? Set. Go. Right. Simple idea. Radio waves, long wavelength, like a meter, right? And then this is the idea. All of it's traveling at the same speed, but they have different wavelengths. Okay? So my energy is going this way, my wavelength is going this way. I've got one more thing that's happening here, and it's frequency. So how often, if I had a continuous beam often does a wave, does a crest or a trough pass through a certain point. That's the measure of frequency. The shorter the wavelength, the higher the frequency. They're inverses of each other, okay? Inversely proportional. So, do we understand a little bit right now the relationship between energy, wavelength, frequency? What happens to my energy if I increase my wavelength? Does my energy go up or down? Energy goes down. What happens to my energy as my frequency goes up? It goes up. What happens to my wavelength as my frequency goes up? It goes down. What happens to my speed as I change as my wavelength goes up?
Nothing.
Nothing. Speed always stays the same, right? What is the highest energy light we have? Gamma rays, which means gamma rays also has the highest frequency and the lowest wavelength. Radio waves have the longest wavelength and the lowest
Energy, frequency.
frequency and energy. Very good. Okay. Another way to look at all this is think, okay, radio waves, microwaves, infrared. We get into what? Red, orange, yellow, blue, green, green, blue, indigo, violet, and we've got ultraviolet, and we've got X-rays, and then we've got gamma rays, right? So this is showing you the same thing as that, but a little more graphically, okay? When we look at the stars, we're looking at light. Is light is light traveling like a rope? I mean, is it literally like if I took a rope and I just swung it back and forth, is that what light is like? No, light is this little point. It's called a photon. A photon is a very discrete bundle of energy. In some ways, light acts like a wave. It goes up and down. In some ways, light acts like a particle. You don't have to know all that. But you do need to know that it's not just some continuous thing. It's this little tiny point of just pure energy. If I increase the energy, that will be manifest in its wavelength and in its frequency, right? But it's always going to travel at the same speed. Okay? Where do photons come from in a star?
Core from fusion.
From the core, from fusion, right? And through a series of reactions and interactions, the wavelength, they begin as gamma rays in the core, right, from fusion. But they don't all, it's not like you're just getting bombarded with gamma rays, we'd be dead. Right? It interacts with other atoms, they absorb some energy, they release some energy, and sometimes, it loses energy. And so it will come out as these different wavelengths of light. And we can measure these. You can see them with your eyes, right? Is every star the same in the night sky? Is it the same color? No, some are red, right? Lower energy? Or, wrong way. Lower energy? Something like Rigel is blue, or maybe even closer to violet, right? Higher energy? Right? We've got telescopes. We can only see this stuff, right? But we have telescopes that can see all of this, and that can see all of this. Now, I've drawn this like it's this big, huge section. The amount of light that we can see actually fits like about here on the spectrum of the whole thing. We can hardly see anything. But stars are producing a full spectrum of light. If we're going to talk about stars, we've got to understand these certain things about light. Okay? So where we'll kind of go from here is we'll look at why stars are different colors, how that relates to their size, how that relates to their temperature, things like that, okay? So let's go ahead and we'll get started with some of that. Can't do that.
Since we've been able to look up at the sun, we've been aware of light. As darkness, very few things that we instinctually fear. We have always bestowed light with godlike properties. But for all of antiquity, we had no idea what light really was. Figures like Newton and Huygens worked with light in the 17th century, but a more sophisticated description of light, which we call classical electromagnetism, was developed largely by James Clerk Maxwell in the 19th century. This theory depicts light as a transverse wave composed of oscillating electric and magnetic fields, which are at right angles to each other and perpendicular to the direction that the wave moves. We will learn more about these fields later. Just like the kinds of waves we have previously discussed, electromagnetic waves have amplitudes, wavelengths, and frequencies. But instead of different frequencies producing different pitches, like sound waves, different frequencies of electromagnetic waves produce different kinds of light. If the light is visible, these frequencies will correspond to different colors. Frequencies greater than this will exist as UV radiation, X-rays, or gamma rays, and frequencies less than this qualify as infrared radiation, microwaves, or radio waves. All of these phenomena are collectively referred to as electromagnetic radiation, and they can be found on the electromagnetic spectrum. Here we can see all the wavelengths and frequencies ranging from radio waves to gamma rays, and we have found some technological use for all of these in modern society. Even though they seem dramatically different, some requiring things like antennas or other equipment to manipulate, all of them are fundamentally the same thing as the light you can see with your eyeballs. They are just of different wavelengths. All electromagnetic radiation moves at the speed of light, which is about 300 million meters per second in a vacuum, the fastest speed possible in the universe. This is fast enough to get from here to the moon in about a second. And since we know that all waves move at a speed that is equal to their wavelength times their frequency, this product will be equal to the speed of light for any type of electromagnetic radiation. How is it that electromagnetic radiation is produced? To answer this question, we have to learn about electric fields, which are coming up soon. For now, let's check comprehension. Thanks for watching, guys. Subscribe to my channel.
We're not subscribing. Let's go here. Give our guy one more one here.
Let's check out some stars.
He knows a lot about science stuff, Professor T explains.
Now that we are about 1 billion years into the history of the universe, we can see a panorama of stars swirling around in galaxies, which have in turn collected into clusters and superclusters. So what happened next? The answer to this question will require that we learn more about stars and their characteristics, which determine the way we categorize them. So let's learn the basics about this system now. When we first started to observe stars in telescopes, we divided them into color classes: white, yellow, red, and deep red. This was later refined, and each color was broken up into letters: A to D for white, E to L for yellow, M and N for red. Later, it was realized that things made more sense if stars were categorized by surface temperature. But this letter system was retained because all the work to classify stars had already been done. So from hottest at around 25,000 Kelvin to coolest at around 3,500 Kelvin, we now have O, B, A, F, G, K, and M stars, a classification system called the Harvard system, which was developed by early astronomer Annie Jump Cannon. This sequence of letters is rather unintuitive, but to remember the order, we can use the following mnemonic. Oh, be a fine girl, kiss me. Feel free to replace girl with guy, depending on your persuasion. Or if you find the whole thing terribly sexist, just make up your own, such as, omniscient beings are firing gigantic knowledge missiles. As we can't stick a thermometer into a star to see how hot it is, this classification, based on temperature, is actually derived from Wien's law regarding black body radiation, which we saw in the modern physics series, as well as other types of data, like emission spectra. We analyze the light we receive from a star and correlate it with a particular temperature, as well as with specific elements, just like when we learned about the Bohr model in general chemistry. The hotter the star, the more of the hydrogen and helium nuclei that have been stripped of their electrons, forming the phase of matter known as plasma. The hottest stars, O stars, show very little hydrogen because most of the hydrogen is without an electron and thus can't absorb and emit light. Helium is still able to retain one or both electrons, and thus we do see emission correlating with helium. Cooling down a little with A stars, suddenly hydrogen can hold on to an electron, so the spectrum changes. Getting cooler still, some bands show up that correspond with metals, like calcium. So the convention is derived from temperature, but this happens to correlate with color and size as well. Hotter objects, like O and B stars, are blue, and cooler objects, like K and M stars, are red. Also, hotter stars tend to be larger and burn brighter, with the additional heat resulting from the fact that so much more fuel is being burned. All of this data regarding temperature and luminosity, as well as indirect information on mass and radius, can be represented on something called a Hertzsprung-Russell diagram, or an HR diagram for short. In this diagram, the horizontal axis shows temperature decreasing to the right, and the vertical axis shows luminosity, or the amount of energy emitted by a particular star per unit time, increasing going up. We can see that the majority of stars fall on a continuous curve, which we call main sequence stars. 90% of all stars follow this trend, including our own sun, which is part of this yellow region here. Some stars, like red giants, are very cool yet luminous, while others, like white dwarfs, are very hot yet dim. But the majority belong to this main sequence. Even though this diagram lists only temperature and luminosity, we can infer many things about other variables. Larger stars are always more luminous, as more surface area means more energy emitted. We can also see color clearly correlating with temperature as we move from left to right. Size is also represented, with main sequence stars decreasing in size from left to right, but with red giants and white dwarfs deviating from this trend. This data, collected by looking at hundreds of thousands of stars in the early 20th century, reveals certain facts about stars, such as the mass-luminosity relationship that we just described. It explains why the blue stars in this corner of the main sequence burn brightest, getting dimmer as we go towards the smaller red stars. This has to do with the fact that the gravity crushing the star inwards increases exponentially with its radius, so larger stars have to generate much more outward pressure to prevent collapse. So that's some basic information about all the stars in the universe. Remember, for the main sequence, blue stars are big and hot and bright, up to about 100 to 200 solar masses.
Let me stop there for a minute. All right, we're going to come back to our stuff. And we'll go back and forth. Okay, I'm going to erase this. We're going to go through what he was just describing. Okay. So, tell me some things that you heard. Anybody?
Size and color correlate to heat and overall environment.
Okay, so there's a correlation between size, brightness, and what all did you say? Size, what else?
Size and brightness.
Brightness, what else?
Correlates on like how light
I
it is.
heard heat or temperature.
Yeah.
And color.
There's one more thing, it's color, right? These are all correlated in some different ways. You talked about stars. We've defined stars as a large ball of
Gas and plasma.
gas and plasma, right? Is it all plasma? No. What makes it plasma? Define plasma. Gas that's stripped of, or ionized gas, right? It's stripped of its electrons. Why can't those electrons stay around plasma?
Too hot.
It's too hot. So the hotter it is, the greater proportion of plasma to gas, right? One of the things that they talked about there is that the really, really hot stars, super hot stars, only show in spectral analysis, and I know we haven't talked about spectral analysis yet, but when you're specifically analyzing the wavelengths, right, of light, the crazy hottest stars, the largest stars, don't show hydrogen. They have it, but they have it as plasma. They don't have it as a gas. And so, because, you know, the difference, right? So you've got this nucleus. Here's a hydrogen nucleus, right? In the gas form, it's going around, the electron gets excited, it goes to a higher orbital, it falls back down, and it releases a photon of light, right? A photon of light that specifically correlates to the signature of hydrogen. But you can only get that in the gaseous phase. You cannot get that in the plasma phase. But for helium, you can get that. And so your biggest stars will show basically no hydrogen, but they'll show helium. Well, your biggest, hottest stars that show almost no hydrogen always come out as what color?
Blue.
Blue or violet, right? So your hottest stars incidentally come out as red, or I'm sorry, as violet or blue. On the complete other end of the spectrum here, your coolest stars come out as red. And in between, we have, you tend to get white, you tend to get yellow, you tend to get orange. And so as my temperature goes this way, my color goes from red, orange, yellow, white to violet. Okay? Another thing that he was talking about there is the correlation of mass, how large it is, right? The reason that the biggest stars don't show this is because they're almost all plasma. The reason they're almost all plasma is because they're so crazy hot. Why are they so crazy hot?
Gravity.
Nick, come on. Come on. Need you. Need to sit?
The,
Can't do it? Alright.
the energy.
Joe. Oh, somebody, come on. I guess we'll just wait until somebody gets over here.
Cool, good?
Thank you, sir. Alright. You're gonna be gravity, right? Say, if we're a huge star, the force of gravity is enormous, right? So you gotta like really, I mean, and so if the force of gravity is enormous, then the force of pressure that comes from fusion, which is heating us up, has to be enormous. Otherwise, we're just gonna get crushed, right? You gotta actually push.
Oh, okay, I thought you were gonna ask me.
I mean, not crazy, but you know, his force is so great because it's so big that if I am not putting out tremendous pressure from fusion, we're just going to get crushed, right? The gravity, the force of the gravity squeezing these together heats this thing up, which provides the initial energy required to get fusion going. Because there's so much of it, so much material, this fusion is just happening. I mean, so fast. Wait, sit down. Okay. So, our hottest stars are also our largest stars. And our coolest stars are also our smallest stars. Okay, does that make sense? Now, there's another thing that we've talked about size, we've talked about temperature, we've talked about color, we haven't talked about brightness. When we began today, we were talking about, brightness as a thing, and we had the idea of, okay, well, is it color that makes it bright? And we said, no, what is it that makes it bright?
Photons.
The number of photons, okay? Okay, so if I have, I've got my phone shining, and I give you this little tiny slit for it to come through. It's not going to be very bright, right? But if I open the slit up more, it's going to be brighter because more photons are used. And if I open up brighter, more photons, right? The larger surface of photon emission, the brighter it's going to be, right? Does that make sense? Okay, so essentially what happens with the brightness of a star is if I have a little star, I only have a little surface for the photons to escape from. But if I have a big star, I've got a much bigger surface for photons to escape from. So though brightness will correlate with color, it's not caused by color. Both brightness and color correlate with size, just how massive it is, okay? So another thing that happens here is brightness. Okay. So two gentlemen kind of working at the same time, they're not together independently. Other guy named Hertzsprung, a guy named Russell, and they both recognize these patterns. And they put together a diagram that you must know. We're going to kind of create it, and then I'm going to give you a professional copy of one, okay? And you will know this. This tells you so much about stars. So do me a favor, draw an axis, okay? Okay. Okay, so on this axis we're going to have our luminosity, which is also means our brightness, okay? And on this scale, we're going to have our temperature. And I'm going to put my brightest, hottest star up here. And I'm going to put my dimmest, coolest star down here. My brightest star is my hottest. It's also my most massive. It's also my most violet. So what direction does this go? It's got to go this way, right? Temperature's got to be increasing as I go this direction, which is not how you are used to looking at graphs, is it? Usually your x-axis is going this way. But luminosity is going this way, right? Okay. So that's the first thing to know here, is temperature on your x, luminosity on your y, and temperature is running opposite of what you expect, okay? So your brightest, hottest stars in the top left, your coolest, faintest stars in the bottom right. All right. Now, size. Let's try to draw these proportionally, right? So we know that our luminosity and our temperature both come from our mass. They come from our size. So I'm going to draw a big star up here, okay? And I'm going to have a little star down here. That one's good. In between, I probably need like a medium-sized star, don't you think? And as I go about this, well, let me try to draw it somewhat proportionally to how it is. I got a blue, so I can do blue. White's easy. I don't have a yellow. I got plenty of red though. Do some orange. Okay. So far so good? So, color-wise, got violet, blue, white, yellow, orange, red. Okay. Okay. These colors correlate to temperature, these colors correlate to size, these colors in many ways correlate to luminosity. We have not drawn every kind of star that there is. We have drawn only stars that are doing fusion of hydrogen to helium in their core. As Cody said, this is called the main sequence. The idea is that every star during its lifetime, during the majority of its lifetime, will be found somewhere on this sequence. How do I know where it is? Well, the number one overriding thing that determines everything else is its mass. The biggest stars are always going to be up here. The smallest stars are always, and by the way, they don't move. They don't change spots on the main sequence. I can't have a little star, or we have no examples of a little star suddenly like gathering more gas and becoming a bigger star, okay? And conversely, a big old star like this, it's not like it just slowly loses matter and gets smaller and becomes like a white star. The amount of mass that it uses, it converts mass into energy, is actually, I mean, it's tiny. It's tiny. The bulk of its mass is simply going from hydrogen to helium. It's still huge. They don't trade spots on this, okay? They don't shift. Now, they can leave the main sequence and go up here or go down here, but then they leave the main sequence. The main sequence is the main sequence because it's saying every star, while it's burning hydrogen or fusing hydrogen to helium in its core, is somewhere along this particular spectrum. If you learn nothing else today, learn that, okay? You need to understand the main sequence. You need to understand these aspects of the main sequence. 100%, you will have to be able to draw this graph. Or if I give you this graph, you're going to be able to label this graph. You're going to have to interpret this graph. You're going to be able to tell me everything that's going on right here. And ultimately, not only this, but you'll tell me where the giants are, where the supergiants are, where the white dwarfs are. You'll tell me all of it. Now, today's not going to be the only day we talk about this. We will probably talk about this almost every day the rest of the year. Because this is not a graph of the main sequence. This is the main sequence portion of the Hertzsprung-Russell diagram, which includes all stars. Okay, so we'll throw the rest of them in as time goes on. Do you have questions right now? Everybody perfectly understands this. You ready for a test?
I have a question, but I mean, I understand that, but it's like on that graph in the video there was green. I've never seen a green star.
There are no green stars.
Okay, just wanted to.
Yeah.
That's a shame.
Yeah.
Good question. Why is violet brighter than red?
Because its frequency is bigger.
Nope.
More energy.
Nope.
More surface for
More.
photons.
Whoever said photons is half there, and whoever said more surface area has the other half, right? More surface area means more photons being emitted, therefore it's brighter, okay? Okay. Now this is a big deal, because you're used, right now, you think, well, violet is the brightest star, right? It's the brightest one on the main sequence. But then we're going to go and I'm going to give you the whole thing later on, and you're going to have red supergiants like Betelgeuse, and it's going to be like off the charts, bright, but not that hot. What does that tell you? Why is it so bright if it's not that hot?
So big.
Size.
It's so big, it has such a huge surface area that these things are, and so you would think, then you got to start thinking to yourself, well, actually, a red giant then, or a red supergiant, must be bigger than this violet star, even though it doesn't have more mass. This has more mass, but this has a bigger surface area. Well, what's going on there? And so we'll talk about these things, we'll learn those things. Or you'll have something like this. We have some stars down here. Well, they're in the white range, and they're small. They're not crazy massive. They're not that bright. What's going on with these? What are these? White dwarfs. They've left the main sequence. They're not as bright because these aren't doing fusion at all. This is, you know how you heat up a piece of metal and you take it out of the fire and it still glows for quite a while?
Mm-hmm.
That's the whole thing with a white dwarf. It's not doing fusion anymore. It's just glowing because it's crazy hot. And over time it'll just cool down and dim down. Okay. What determines its temperature?
The color?
Nope.
The mass?
The mass. That's another thing really we need to understand on here. Mass. Mass and temperature on the main sequence anyways are directly correlated. It's a one-to-one relationship. More mass equals more gravity, and as gravity pushes in, it equals more pressure. As that pressure pushes in, it induces fusion, and to counteract the force of gravity, you've got to have a lot of force of pressure from the fusion, right? So the more massive you are, the more fusion that's happening. Let me ask you a question. Is there more energy in a gallon of gasoline or in a twig? Which one has more energy? You're going to burn them both. Which one has more energy? Total energy. A gallon of gasoline or a twig? It's not complicated. This is not a trick question.
Gasoline.
Yeah, by a lot, right? Gasoline has a ton more energy than a twig. I'm going somewhere. I'm not that dumb. Ready? Which one's going to burn faster? The gasoline or the twig?
Gasoline.
Oh yeah. Even though there's so much more of it, it's going to burn so much faster. Which one of these is going to last longer on the main sequence? A purple or a red?
Red.
A red. This has so much more mass, but it's doing so much more fusion that it literally burns itself out. These, going. I mean, in the whole tortoise and the hare thing, like these are your tortoises, these are your hares, right? They're gonna slow and steady. That thing's gonna burn itself out like that. Okay. All right. What time is it? I'm gonna dive into anything else. Let me give you one more thing for today, and then we'll pick up again next class. He talked about this spectral class stuff and colors, and they categorized stars by colors, and they assigned them letters, and then they realized later, like, oh, the color is not really a good, like, the colors don't correlate to anything. It all correlates to temperature. But they realized that the colors and the temperature, it just got weird. They used to do them something like this. The colors would go like maybe A, B, C, D, E, but this didn't work out like that. This worked out when they took their color scheme and they applied it here. They found that it went O, B, F, G, K, M. Totally out of order. But because they've been doing it forever, and they didn't just want to throw out, you know, over 100 years worth of data on hundreds of thousands of stars that they've collected data on, they kept it. They just put it where it should be. Do you actually need to know this? Well, I'm going to make you know this because we're doing astronomy, and this astronomy, like astronomers do this. Okay? So this related to a system of color, not a system of mass or temperature or brightness. Okay? In order, that means that your purple stars, your biggest purplest stars are O's. Your smallest, reddest stars are M's. And in between, you've got something like a G, which is going to be on the yellow range of things. Somewhere right in the middle. I've told you before, where's our star? It's yellow, right in the middle. We're a very average star. We're a G class star. Okay? So that's one thing that's helpful. Here's our sun. We are a G class star. The mnemonic device they gave was "Oh, be a fine girl, kiss me." It works because that's how I just remembered it. Don't think I just know these in the right order. I have to sit there and think. Oh, be a fine girl, kiss me. This in order from most violet to most red. That's how it goes. Okay. Next class, see. See. If the heat's working, then we will have class next time. If not, we won't. But if we do have class next time, or whenever we do get to our next class, we will look at how we're getting these colors. Why is a purple star purple? Why is a red star red? What's happening with hydrogen and helium and all these other things? We'll look at we'll look at the idea of spectral analysis and dark line emission and bright line spectra and all this stuff. All right. Y'all have a good day.